we go. All right. So this chapter, 6A, is all about identities. We actually talked a little bit about identities in chapter 5 briefly. So if you look at the top left corner of your identity sheet here, the formula sheet, the first three groups should be familiar to you. We talked about reciprocal identities, we talked about quotient identities, we did the Pythagorean identities, and then actually at the very bottom of the page on the left side are those co-function identities that we had talked about also. So some of those are not new to you. Today we're going to be adding in first the even odd identities, the ones that you know, and then that, top quarter on the left side is what makes up what's called the fundamental identities. That's what section 6.1 is, just that top corner. From there, then, in the next few sections, we're going to add a few identities in as we go. And so we'll learn some new formulas and we'll practice. And we'll get a new set of formulas and we'll practice. As far as like testing with the formulas, there's two types of tests you're going to take in this chapter. The first one is a memorization test. And it says on your calendar what day that's happening. That's the identities test. The memorization test will be every single one of these, and it's going to be a fill in the blank, where I give you half, and you fill out the other half. Then, for the other portions of the test, you will be given this paper. Okay, so for when you actually have to use them and do calculations, you will not have to have these memorized. You'll already have done that on a separate test. So we're kind of like splitting the work here. Memorizing it, showing me you know it on one day, and then I'll give you the formulas to work with, do calculations with on the next day. And then you'll have, of course, a blank unit circle too if you want it. Okay. So that's coming up. I think you've got like 3 or 4 weeks till that comes up. We've got a while. Just a little heads up about that. There is a Quizlet. You can make flashcards as you go, and just as we add a couple in, just practice with them, or you can do it all at once at the end. It's up to you. All right, so we're going to add in first a couple things on your sheet. So number 1, reciprocal and quotient are there already. Pythagorean identities are there already. In the margin on your paper, next to the Pythagorean identities, the first thing I want you to do is write these equivalent forms, okay? Anywhere you can fit them in the top corner there. So if I take like sine squared plus cosine squared equals 1, and I, let's say, subtract sine squared on both sides, if I just move stuff around, then I would end up with cosine squared equals 1 minus sine squared. Okay, so it's an equivalent form of that same formula. It's just something moved from the left to the right or from the right to the left. The reason you want to write them down is because we won't always see sine squared plus cosine squared. We might see 1 minus sine squared, or we might see 1 minus cosine squared, and we want to be able to recognize that that is a Pythagorean identity. Things are just moved around a little bit. So having them written down will make that recognition piece maybe a little easier as we see those in problems. Okay, so I'll give you a second to write those equivalent forms down. And then we're going to get to those even odd identities for both those things. Okay, everybody have what they need? Anybody need more time? A little more time? Okay. Okay. All right. So those make up our fundamental identities plus these guys, which you will see on your paper, are the even-odd identities. Okay, so even-odd identities, if you guys remember when we did all of our trig graphs, sine, cosine, tangent, all those things, one of the things we added onto the graph was if it was an even or an odd function, and that is where these formulas come from. Back from college algebra, we said that a function was even if when I plugged in a negative, it simplified to the original function. Okay, and that was like a little formula that we had there. And we said if it was odd, when we plugged in the negative, it simplified to the opposite of the original function. And then we could also look at the graph and say if it was symmetric to the y-axis, that was even. So we marked those on all of our trig graphs. And if it was symmetric to the origin, it was odd. And if it was neither, it was neither, right? Okay, when we looked at all the trig graphs, we labeled even or odd for each of them. And we figured out that cosine and secant were the only two that were even functions. If you look at those graphs, they are symmetric to the y-axis. And that also tells me if they're even functions, I can write it like this. I can plug in that negative, and it simplifies back to the original function. The other four functions are all odd, which means when I plug in a negative, it simplifies to the opposite of the original function. So you'll see the difference in the two sets there. So how do these formulas help us? It helps us if you have a negative inside the trig function, simplifying it. You can either, if it's even, get rid of the negative, or if it's odd, bring the negative out front of the function. Those are the two things we want to think about, okay? So there's just some practice ones here. These are really just unit circle questions. When we did these before, if it was a negative, we would just add 360, right? And that is fine. You can do that. But we're going to practice just how these formulas would work, okay, with this. And you can do it with radians. I've just got a bunch of degrees here. So the first one I'm going to look at is sine negative 135. So sine is an odd function. Because sine is an odd function, I can write this instead. Instead of sine negative 135, I can write negative sine 135. And then I can find from my unit circle the sine of 135. I can save myself the step of having to add that 360 over and over again. What is the sine of 135 from your unit circle?
Square root 2 over 6.
Square root 2 over 2. And it's positive because it's in quadrant 2. All we have to do is make it negative, and that's our answer. Okay, just change the sign. That's what that negative out front tells me. Yeah?
Wait, so how did you know sine is odd?
That's up here. Do you see that? Yeah. So that tells me I can bring the negative out front. It's also, I mean, if you didn't label that it was odd, at least if you saw in the formula sheet, oh, what can I do with that negative? I can bring it outside the function. That's fine, as long as you recognize that. Cosine and secant are the only two that are even. So let's look at the next one. Secant is an example of an even function. If it's even, the negative inside, we can pretty much just get rid of. It simplifies back to the original function. So this is exactly the same as secant of 210, if I recognize that. And I don't, again, have to add or subtract anything. What's the secant of 210? What do you think? 2 over square root of 3, so close. 210's in what quadrant? And if I'm in the third quadrant, secant's a reciprocal of cosine, right? Is cosine positive or negative? Negative. So it would be negative 2 over rad 3. So cosine there is negative rad 3 over 2. Secant then would be the reciprocal, negative 2 over rad 3. And then if we rationalize, negative 2 rad 3 over 3. Okay. Tangent, negative 45. Is tangent even or odd? Odd, which means what can I do with that negative? Bring it out front. Negative. Tangent 45. What's the tangent of 45? 1. So my answer is negative 1. Cosine 330. Cosine even or odd? Okay, so what do I do with the negative? Drop it. Cosine 330. All right, what is the cosine of 330? That's the x coordinate.
Quadrant 4, so it's going to be positive, right? Rad 3 over 2. The sine is a half, negative a half. Cosine's rad 3 over 2. Remember, imagine that point, long and then short to get to it. Cosine's the x. Okay? Understand how these work? Yes? Okay, good. All right. So that was like just the little, I guess, background information we needed to be able to do these problems today. We need to understand how all 4 sets of fundamental identities work, okay? So for all these problems, you, again, are only looking at that top left corner of your paper. So we're thinking about reciprocal, Pythagorean, quotient, and even odd. Those are like our only tools in the toolbox right now, okay? Everything else you can just ignore on that paper. Our job is to use those and our algebra skills to be able to simplify these little expressions as much as possible. So that's what we're going to practice with today, okay? So go ahead and write that first one down. Sine cubed plus sine times cosine squared. There's not going to be a whole lot of numbers in simplifying in these, like with unit circle values. It's more so just being able to manipulate the trig functions, okay? So sine cubed plus sine times cosine squared. An example of how I can manipulate this, think of the sine and cosine just kind of like an x and a y, okay? I have an x cubed plus an x times a y squared. Those terms have something in common, right? Like I have 2 terms added together and they both have some x information, or they both have a sign in them. So back to algebra, like algebra 1, if you had 2 terms with something in common, what would you do? We could combine if they were exactly like terms. They're not, though. So what else could you do, such as an f? Factor. You can factor out something they have in common. What do these 2 terms have in common? A sine. Okay, so let's take a sine x out. Okay, so if I take a sine out of a sine cubed, what am I left with? Sine squared. If I take a sine out of sine cosine squared, what am I left with? Plus cosine squared. Okay, so that was just an algebra step. No trig identities necessary. Then we want to look at, can we use more algebra or can we use a trig identity? This is an example of something that you should recognize from your sheet. Sine squared plus cosine squared is the same as what? So we replace it. Anytime you can replace with a trig identity to make it simpler, you want to do that. So in the parentheses, I'm going to put a 1. And anything times 1 equals, it's L. And then once you get down usually to a single value, a single trig function, or as few trig functions as possible, if you can't combine anymore, that's as far as you can simplify. So that's where we would stop, okay? So our answers to these aren't going to be like a nice pretty number in most cases. Sometimes it could be, but for most of it, it's going to be something like this, okay? Let's practice another one. This one, it's a little weird how it's typed there. This is what it looks like. Secant x plus 1, secant x minus 1 over tangent squared. Okay, that's what the problem is. Okay. That numerator, let's just think about some algebra. If I've got 2 parentheses multiplied together, 2 binomials multiplied, what do you do with that? Just algebra. Foil. That's what we're going to do. Let's foil. And we're foiling conjugates, if you recognize. You get the same terms but different signs between them, 1 plus, 1 minus. Do you remember what happens if you foil conjugates? If not, let's do it. What are the first terms going to give you? Secant times secant. Secant squared. My outside term, secant times -1, negative secant. My inside terms, 1 and secant, secant. Last term's 1 and -1, -1. What happens? Outside and inside cancel. Did you have a question? Oh gosh, I wrote tangent and it's sine. I'm sorry, guys. Wasn't even paying attention. Okay, so that's actually, if you have conjugates, only conjugates, same terms, different signs between them, the outside and inside are going to cancel. So you could save yourself a little bit of time and just do first and last if you recognize that. All right, and then I still have sine squared on the bottom. Okay, so now I have secant squared minus 1 over sine squared. Are there any trig identities that you see there, or equivalent forms of trig identities? What is it? Yes, secant squared minus 1 is one of the equivalent forms you wrote down. It is equal to tangent squared. Now I have over sine squared. Now I have to figure out how to put these together. Okay, one common thing we use if we are simplifying trig functions and we get stuck, doesn't always work, but it's a good thing if you get stuck, is every trig function can be written with either sine or cosine. So sine is itself, cosine is itself. Cosecant and secant are the reciprocals of sine and cosine. And tangent and cotangent are either sine over cosine or cosine over sine. So if I want to be able to figure out how to put this tangent and sine together, I'm going to take tangent squared and I'm going to rewrite it as what it is with that quotient identity. Tangent is sine over cosine. So if I have tangent squared, I have two of them. Sine squared over cosine squared. So that's my numerator. Denominator is still sine squared. If you're dividing fractions, it's a little gross to look at this. So what's the alternative? How else can I rewrite it? Divide fractions or multiply by reciprocal. Okay, so let me write it that way. Sine squared over cosine squared from the numerator. And then instead of divided by sine squared, I'm going to write times its reciprocal, 1 over sine squared. What's going to happen there? The sines are going to cancel, and I'm left with 1 over cosine squared. Well, if it was just 1 over cosine, what does that simplify to? Secant. So if it's 1 over cosine squared, what does that simplify to? Secant squared, and that's our answer. You can get it down to, again, a single trig function there. So that's an example of one that's a little bit longer. That's going to involve several steps. Sometimes you're going to start and it's going to be 1 or 2 steps, that's it. Sometimes it'll be 5 or 6 steps. Just depends what math you have to do in the work and what trig identities are applicable. Yes? The x is the angle. No, it doesn't. I mean, as far as like our calculations go, it doesn't do anything. Now, we're going to see problems eventually that have an x for an angle and a y for an angle. So that's going to make a difference in how we simplify because we won't be able to put them together. They're not the same. But for right now, no matter what your angle is, you're going to see it's the same throughout the whole problem. So it might be an x, it might be a y, it might be a theta. Okay? All right. Let's try, actually, let's do the one on the right first because that's actually a little easier, even though it doesn't look like it. Okay? So I've got secant squared u minus tangent squared u over cosine squared v plus sine squared v. Lots of different trig functions here. So I would look at my identities and see if any of those are going to be helpful. What do you see?
Secant squared minus squared equals 1.
Yeah, and as long as they're the same angle, which they're both used, we can use that identity. So secant squared minus tangent squared, that's one of the alternatives. The numerator is just 1. What about the denominator? Cosine squared plus sine squared. That's also 1. 1 divided by 1 is? Final answer. See, that wasn't too bad. All right, let's try the next one. 1 plus tangent over 1 plus cotangent. If it was 1 plus tangent squared, we'd have an identity. It is not squared. Also, This is not two sides of an equation. You are not allowed to square anything, and you are not allowed to square root anything, because that's something that we do to both sides of an equation. And again, you don't have an equation. It's an expression. Okay, so maybe note to self, don't square and don't square root. It's tempting to want to do that, because if you had a squared, your life is a whole lot easier right now, but you may not. Okay, think of that as an illegal simplification rule. No squaring, no square rooting. All right, so I've got to figure out how to write these or combine them in some way. Tangent and cotangent are reciprocals of each other. So an option is, instead of cotangent, I could write what? What's another way to write cotangent? I could write cosine over sine, but I don't have any cosines or sines here. I have a tangent though. I could write it as 1 over tangent. Now let's say you chose to write it as sine or cosine over sine, and you wrote tangent as sine over cosine. That's fine. You're going to eventually get to the same answer. There's going to be more than one like path to lead to where we're going here. I'm just giving you some different examples, okay? All right. The next thing I want to be able to do is I want to multiply by the reciprocal on that denominator to be able to simplify it, but I got to put those pieces of the denominator together first, this guy and this guy here. What do you need to be able to add fractions together? Common denominator. Okay, so just in the denominator, in this part, what's the common denominator? Tangent. Okay, so I'm going to keep the numerator the same. Nothing's going to change there. But instead of 1, I'm going to write tangent over tangent. Something over itself is always equal to 1. And I'm doing that to get that common denominator, and now I can add them together. So my denominator is a single fraction now, 1 plus tangent all over tangent. Now instead of dividing, I can multiply by the reciprocal. So I have 1 plus tangent on top times, again, instead of dividing by my fraction, I'm going to multiply by the reciprocal. Tangent on top, 1 plus tangent on the bottom. What's going to happen? 1 plus tangent is on the top and the bottom. It is a factor of the numerator and denominator. So it cancels, and I'm left with tangent, and I'm done. Okay. I'm going to show you what this problem would look like. Let's see if I can get it here. If I did it with sines and cosines instead, just to give you an example of what it would look like if you did one problem 2 different ways. Okay. Let's see if I can paste it in there. There we go. Okay, same problem. Let's say I did this with sines and cosines instead. So, what's tangent in terms of sines and cosines? Sine over cosine. And what's cotangent? Cosine over sine. Oops. 1 plus cosine over sine. Okay. Now, again, I've got some kind of messy things happening with fractions, so I want a common denominator, and I'm going to do it on the top and the bottom. On top, I need a cosine, so I'm going to write cosine over cosine plus sine over cosine. On the bottom, I need a sine to be able to put them together, so sine over sine plus cosine over sine. So now I've got those common denominators. My numerator, I'm going to put in parentheses just so it makes sense, is cosine plus sine over cosine. My denominator is sine plus cosine over, I did something wrong there. What did I do? Oh, I wrote a sine, a cosine instead of a sine. There we go. Over sine. Okay, so I got common denominator in the numerator was cosine. Common denominator in the denominator was sine. I added them together. Now instead of dividing by a fraction, what do? Multiply by the reciprocal. Numerator is going to stay the same. Cosine plus sine over cosine. Times, flip the denominator. Sine over sine plus cosine. What cancels? Sine plus cosine is the same as cosine plus sine, right? Addition, order doesn't matter. And I am left with sine over cosine. And what is sine over cosine? So did I get to the same place? Yes. Did I use a different method? Pretty much. Yeah, I did sines and cosines instead of a reciprocal identity. So there's not one right way to do these, which is good. And sometimes that can be frustrating too, because I can't say for this problem, this is the way to do it and follow step 1, 2, 3, 4, and that's always going to be how it works, because it's not always how it works. So it's all about recognizing your identities and really being good with like your algebra 1, algebra 2 skills, like the foiling, the reciprocals, the factoring, all that's going to come back now. There's just not going to be numbers. It's going to be trig functions instead that you're doing it with. Okay. All right. Let's look at an example that would have a negative inside the function. Okay, like our even odd identities. That's where we want to focus in. If you see a negative angle, negative x, negative y, negative theta, u, v, whatever it is, the first thing you're going to go to is the even odd identities, because those are the only identities that have a negative angle in them. Okay? Is secant even or odd? It is even, which means what can I do with that negative? I can take it out. That's going to be the first thing I'm going to do. If it was odd, I would just move it out front. Okay. Again, nothing is squared here, and you can't make it squared. So we're going to ignore our Pythagorean identities, although tempting. All right. So what's another strategy we could use? Doesn't look like they have anything in common. What could we try? Angela? Okay, right, secant is 1 over cosine. And then could we write tangent another way? Sine over cosine. What am I missing that would maybe make my life easier right now? Like what one piece is making this messy? The +1. Can we rewrite that another way that makes our lives less messy? Yeah, let's rewrite that as cosine over cosine. And then look what you have here, guys. Do you see that every single term has a cosine in it? At this point, and it's all in the denominators, at this point, you can actually just reduce this fraction. Those cosine denominators are actually just going to cancel because we're reducing the fraction by a factor of 1 over cosine. It's a common factor that's canceling on top and the bottom. So what am I left with on top then? Sine plus cosine. And the bottom is 1. Are those squared? They are not. So can I cross them out and say equals 1? Am I allowed to square them? No. This is as much as you can do. Final answer. So sometimes it's 2 functions. Can't put them together. Yes?
So at the beginning when you have secant, like it's odd.
Even?
Or even, I mean.
Okay. Secant and cosine are the only 2 evens. Everything else is odd. All right. Why don't you guys try the next one? If you want to phone a friend, these are great group work problems that you can like kind of talk out strategies. See what you can do. I'll give you a few minutes. Maybe another one to try. We'll practice. Sine is the correct answer. Okay, here's how I did it. Again, not the only right way. I wrote everything with sines and cosines because there's a lot of different trig functions. There's a lot of different trig functions after this strategy because then it's all sines and cosines at least, and you have more opportunities to combine. Okay. In this fraction, the cosines cancel, leave me with 1 over sine. Here, nothing cancels. You just got to do the multiplication. So cosine times cosine gives me cosine squared. Sine's on the bottom. So cosine over 1, right? Just times sine. Then I have a common denominator. So I put them together. And then this is the key. You got to recognize that identity. 1 minus cosine squared is equal to sine squared. That's an alternate version of the Pythagorean identity. If you have something squared over itself, it's like a sine times a sine over a sine is what we have right now. One of the sines is going to cancel. Just sine.
1 minus cosine squared is just equals 1 squared.
Equals sine squared. Yeah, do you see that on there? 1 minus cosine squared. There's one of your options. Okay, any questions on that?
Do you want to do another one to get, yeah? Uh-huh.
So like, how do you know what you're, like, what to do?
You're gonna, the more you practice this, the easier it's gonna get. 'Cause you're gonna recognize, I promise you, you're gonna get to the point, you're gonna be like, oh, 1 minus cosine squared, there's a 1 and it's squared and it's a Pythagorean identity, and I know to look and replace that as soon as I see it. Or if I have a lot of trig functions, I'm gonna use sines and cosines. It's gonna take practice, but we use the same sort of strategies over and over again, okay? Do you want to do another one together or try another one on your own?
Another one on your own.
Together? Is that what we're voting on or on our own? On your own? Okay. Which one do you want to do, left or right? Left? Sure. Go ahead. You can try both of them if you want to.